Welcome to a KNAUER HPLC columns tutorial with the topic reversed phase columns and stationary phases. As you might know, reversed phase columns are most often silica gel based columns. If you want to know the difference between different support materials for stationary phases, you're highly invited to watch our video about the differences of stationary phases. So there are silica gel-based phases and also polymer gel-based phases. But in this presentation, we want to focus on the reversed phase columns that are in the KNAUER column world always based on silica gel. As you might know, there are a lot of different reversed phase columns on the market, and they have a lot of different modifications. To give you an overview of what KNAUER typically offers, this is a table from our Eurospher II modification types. So Eurospher II is KNAUER's most often used stationary phase, and here you see all the different modifications that we offer in this column family. They can be divided into unpolar bonded phases. So these are typically phases used for reversed phase. And the other ones are more polar phases that are typically used in normal phase or in helic mode. And as you see here, most of these phases are reversed phase materials. And you also see that there are a lot of different C18 columns, but also different modifications. And we just want to shortly tell you why we have this broad range of reversed phase stationary phases. But first of all, what is reversed phase? So when do we talk about reversed phase? The word reversed phase just comes from the word normal phase. So just the first chromatography that was ever done was done on a so-called normal phase material, and it's called normal phase because it was the first. It's not the one that's normally used because reversed phase is most often used today in HPLC. So normal phase is something like the other way around than the reversed phase, and because of that we call it reversed phase. What is the stationary phase here? It's an unpolar material, and most of you might know the typical C18 phases. They are most often used in reversed phase. They are really popular. The mobile phase is more polar. So you have to get a difference between the stationary phase and the mobile phase to take the advantage of a reversed phase separation. And typically analytes that you can put in this mode, you can analyze in this mode, are some kind of mid-polar to mid-unpolar analytes. They have to be soluble in the typically used polar solvents. So a really often used solvent is water mixed with an organic content, for example, acetonitrile or methanol. And your analytes have to be soluble in that, of course. Otherwise, you can't use this mode. I don't know if everybody is so familiar with it, so I just want to show you shortly what a reversed phase is. So what do we chemically do when we produce a reversed phase particle? So you always start with something like that. This is a schematic drawing of a silica gel particle, and you have everywhere on the surface this little silanol groups. They are free, so nothing is bonded on here at the moment. And just imagine this is most often a fully porous particle. So you don't have one sphere. It's just a schematic drawing. Typically, it's everywhere there are pores going through the particle so that the surface is really high. But here, just to show you how it works, I made a really easy kind of graphic. So in the first step, you take this particle that would be, if you would use it like that, would be a normal phase particle. But now we do a reverse phase modification with it, so you can use it in the reversed phase mode. And what we do is we want to exchange a lot of these polar groups with something really unpolar. So we do a first modification And I show you the C18 one because it's just most often used. So these are chains of carbon molecules brought on the silica gel particle. With this step, you can cover a lot of the silanol groups, but not all. So you see still some silanol groups are here on the particle. So still some polar groups are there for interaction with analytes. Most often this is not really wanted. If you produce a reversed phase particle, so you can do a second step and bring a different group on it, and this is called the end capping. By end capping, we mean you do the same again as in the first modification step, but you don't take these long chains of C18 because you won't cover a lot of more of these groups just because of the steric interaction. They can't reach the particle anymore, but these small groups that are typically shorter C chains or just little unpolar groups, they can go through here between the chains and just cover a lot of more groups here. So you see, still some silanol groups are free, but some are also covered. And this is what we call the end capping step. And this would be a classical end capped C18 stationary phase. Okay, but the question, of course, is what is the retention mechanism now happening on these reverse phase columns? So what does an analyte see when it comes for separation on this column? This is really complex, and there are a lot of different things and mechanisms are involved. I just want to show you the three most important ones that are really defining the selectivity of a column. So first of all, of course, we have the hydrophobic interaction. So this is what an analyte, here this little red guy, is experiencing with the unpolar chains. And this is what we want when we produce a reversed phase particle, because we bring these chains on here to have this hydrophobic interaction between the chains and the analytes. And on the other hand, we also have a steric selectivity by bringing these chains on the particle. So for example, smaller analytes will stay a lot longer on this column, because their way through the column is much longer, because they always go between the chains and out again, while a larger particle can't penetrate all these spaces between. And the steric selectivity is really made up by the column, and depending on how hard these chains are standing in the room, so something like a brush type column where it's really, really strong, or if they are really soft and the chains can go a little bit side by side, there the steric selectivity won't be that high. And the third one that is really important is the hydrogen bonding capacity. This is called what happens with the resting silanol groups on your silica gel particle and the analyte. So it's something opposite of this hydrophobic interaction. It's something like a hydrophilic interaction or a polar interaction. And some molecules, have different places on the molecule. So some are acting with the hydrophobic groups, and some places are acting with the silanol groups. Or you have a mixture of analytes in your sample that need both. So some are really polar, some are more unpolar, and you can analyze both of them with these reversed phase columns that still have a little polar interaction here. So this is something also that characterizes your reversed phase column. Yeah, but coming back to our Eurosphere 13 modification types, you still see we have 4 different C18 modifications. And I just told you about C18 columns. So what is the difference here? And why do we offer these different types of C18 columns? So this is what is our classical C18 mode. Here we have exactly what I told you before. The silica gel particle, C18 chains on it, and one end capping step to cover some of the silanol groups. Then we have something that's called the C18A phase. So here you do in the first step exactly the same. You bring C18 chains on your particle, but in the second step, you use for the end capping not an unpolar group, but a little polar group to cover some of your silicon groups here. And this is something really interesting because you enhance the polar interaction. So here is a phase that combines the polar and the unpolar interactions in one column. Then we have something that's called the C18H phase, and the H here is for hydrophobic. So what we do here is we take exactly the same particle as here, also with the first end capping step the same, but here we take a second end capping step. So here we cover nearly all of the free silicon groups, and we minimize the polar interaction and we maximize the hydrophobic interactions. So this would be a perfect column for really hydrophobic molecules that need a lot of these interactions. And the fourth one is the C18P. And here the P stands for polymeric. So here we have a polymeric end capping. Again, we take this C18 particle with the end capping. You can see it here. But in the second end capping step here, we do a polymeric end capping between the chains. So this leads to a really high steric selectivity of this column, because you can imagine these chains are really, really hard standing in the room and can't collapse so easy. This leads on the one hand to a high pH stability, and on the other hand to a really good steric selectivity. But talking a little bit more about when these columns are used. So I brought for you some examples. A classical C18 column can be used for a lot of analysis. So it's really widespread on the market, and we analyzed, for example, this molecule, very well-known penicillin. It is kind of polar, kind of unpolar, has different places and can be analyzed perfectly on C18. This is also caused by the fact that it is soluble in mixtures of water and acetonitrile, for example. No problem. If you have a molecule that is only soluble in pure water and you have a problem when you give organic content to it, you will have a problem on C18 phases. If you would try to use a classical C18 column with pure water as a mobile phase, what would happen? So here you have your C18 chains, and here the element is flowing, the pure water element. And of course, it wants to go between all the C18 chains to cover all the room, but that is not possible because it does not want to interact with these hydrophobic places. So what happens here, the chains might collapse and you might break your column forever. So sometimes it's even irreversible, and your column will not work anymore very well because you won't have these chains anymore. You will have something that is completely lying here on top of your particle. And this is something you don't want to do. So for flushing for a short time, normally it's not a problem with the C18 phase and pure water, but never use it as an eluent for a lot of analysis. That is not recommended. If you want to do that, so if you have something that's only soluble in pure water, please use the C18A modification. So this is what we saw before. C18A has these polar groups in between the C18 chains. And here the water can go between the chains because the polar water wants to interact with the polar groups here, goes between the chains, goes out again, and it's no problem. This is why we call this phase a C18A phase, and the A is for aqueous. So C18A phases can be used with pure water as a mobile phase, while I would never recommend it with a classical C18 column. And for example, a typical application is here acetic acid. This molecule you will never get happy if you try to analyze it on a C18 phase because you need pure water as your mobile phase, otherwise you won't get any retardation on the column if you try it in reversed phase mode. If you use a C18A column, you can do that. You can analyze it, you can use pure water, and it will work. So whenever you have something that is only soluble in pure water and you want to use reversed phase, you have to use a C18A phase. Now, for the C18H phase, it's the other way around. You can use really unpolar analytes. We analyzed DNOP, for example, and here you see it has a lot of places where it's not so polar, and this works fine. Another advantage of this column is also that it has an extended pH stability, because no mobile phase really gets on the particle. Everything is covered here. So this one is much more stable in high or low pHs than the classical C18 phase. And what about the C18P? So I told you before, this has a steric selectivity that is much better than for classical C18 columns. And here we analyzed these two molecules that differ only in some conformational things here. And they were not separated by a C18 column, but the C18P column could do it. So here we used the steric selectivity to analyze these two molecules. Coming back again to our overview, you see there are even more different stationary phases that can be used for reversed phase that are not C18 based. They are not really as often used as C18 columns, but still they are very important because sometimes they work really well. And we just want to look shortly how they look like. So this would be a classical C8 phase. This is the same as the C18, but the chains are shorter. You don't have 18 C molecules, you only have 8. And an end capping here, again, the same classical C8. We also have a C8A phase. This is corresponding to the C18A, but also here the shorter chains. So it's really, again, more polar than the C18A phase. And sometimes this brings you better results for polar analytes. We have a C4 phase, again, shorter change, only 4 C molecules, and something special, the phenol phase. So here you have the ring systems brought on instead of linear carbon chains. So when to use which one? C8 is just a little bit more polar than C18 because the carbon content, of course, is lower, the chains are shorter. So we analyzed, for example, this small molecule here. It wasn't so well separated on C18, so we just tried a little more polar C8 phase and it worked well. The C8A phase, again, for even more polar molecules, we had this sweetener here. It is really only soluble in pure water, otherwise you don't get any separation. So we tried the C18A phase, didn't get such a good separation, and then we tried the C8A because it's again more polar, and here we had a very well separation. So this molecule was perfectly separated here. C4 is something completely different. It's normally not used for the same analysis as C8 or C18 columns. Just remember, it's typically used for small peptides. So small peptides don't really interact a lot with the long chains. They are, compared to other small molecules, they are already large, and they are analyzed often with C4 phases. And this phenol phase can, of course, be used with something that also has a lot of this aromatic systems. So, for example, these two molecules, we could analyze very well on this column because you see again, they are not so different from each other, but they had to be separated. And here we use the PP interactions on these ring systems, and we got a little better separation than on any other column, so we used it. So these were all our reversed phase columns, and now maybe you want to know how can we compare these with each other. So is there a test existing that shows me differences between the different modifications? And there is a very well established test. It's called the Tanaka test, and it was published already in 1989, so it's very, very well established. And a lot of column manufacturers still do this test, so it's very strict. You have a prescription what you have to measure, under which conditions, and then you can get results from these tests and compare them to other columns. We did this for all our Eurosphere II phases and also for some of our other columns. These are 6 tests you have to do, and if you do these tests, you get numbers, and you can put these numbers in a diagram. And this looks like that. This is called a Tanaka plot, and you see here all the tests that you do. So you look for the hydrophobic retention, the hydrophobic selectivity, the steric selectivity, the hydrogen bonding capacity, and ion exchange capacities at different pH values. So I know this is really not so easy. We made here an overview from our phases that you saw before, and you see which one has a higher hydrophobic retention, which has a higher polar retention. But I don't know if everybody can take so much information out from this. And as I told you before, the most important things are hydrophobic retention and hydrogen bonding capacity, and maybe the steric selectivity. But if we're first looking at hydrophobic and hydrophilic interaction of columns, we can take also these 2 values and just plot them against each other to compare columns in something like a more easy way, because it's just a good starting point to watch these 2 interactions for reversed phase columns. If we plot these against each other, so we have here the polar retention and here the hydrophobic retention, values coming out from the Tanaka plots. And if we would plot both against each other, you will have an area over here that can never be reached by any particle. You can't have complete, perfect hydrophobic and hydrophilic retention completed. That won't work. So in this, we don't expect any columns to be. Standard C18 phase would be here in the middle. More hydrophilic ones would have a high polar retention and a low hydrophobic retention. And the more hydrophobic C18 phases, it would be the different way around. So you would have a high hydrophobic and a low polar retention. And we did this for our columns. And you see, if we plot them here, you see that we cover a lot of space here with our Eurosphere II phases. So this means that for any application, nearly any application for reversed phase, you might find in the Eurosphere II portfolio a well-working column. Of course, it's something you have to try. Our application department is always trying to find the best column for applications, and sometimes they have to check a lot of them. But in the end, because of this widespread, you might find the perfect one in this portfolio. But you also see, for example, here in the middle, there is nothing. And also here there are spaces we can't cover. And sometimes this is really what you need. Sometimes you have a separation that's not working between 2 or 3 molecules, and you need a different column. And this is why we don't only offer this one brand, but we also have different columns in our portfolio. So if you see this here, we offer also prontosyl columns or nucleosyl columns, and it's just the case to have the whole range here covered. So it's not to make a confusion for you to offer so many different columns. And also all the manufacturers on the market, they don't put all their columns on the market just to have a new product or just to get attention. It's really most often the case that they are filling a gap that is not there right now. And you see different columns that are also only called C18. So if you use Eurosphere II C18 or nucleosyl C18, they are not the same. So you have different selectivities just caused by the brand name, because chemical modifications are done a little bit different. Yeah, and I hope this gives you a little idea why there are so many different columns, and especially why in the reversed phase range we have so many different stationary phases on the market. Yeah, I hope this gave you a good overview. If you have also interest in normal phase columns, helic columns, or polymer-based columns, please feel free to watch our other videos that are dealing with this topic.